When you buy a new phone and see a spec like 3.3 gigahertz, it's easy to picture a single, glowing, omnipotent brain under the glass, ready to conquer any task you throw at it. But the central processing unit, or CPU, doesn't actually work like a human brain. It operates more like a highly organized general manager. It runs your operating system, handles background calculations, and tracks your keystrokes. If you zoom in far enough, this general manager is really a massive, intricate collection of microscopic transistors. And physically, these transistors do exactly one thing. They switch on and they switch off. This is a schematic of a basic transistor gateway. When high voltage passes through, the switch opens, registering as a 1. When voltage drops, it closes, registering as a 0. This rapid-fire binary logic is the absolute foundation of all digital processing. Notice how the toggling animation becomes a continuous wave. One full sequence from 0 to 1 and back again is a single cycle. So when a spec sheet boasts 3.3 gigahertz, it simply means that the CPU's microscopic switches are completing 3.3 billion of these cycles every single second. Executing billions of calculations per second sounds like enough power to handle anything. But raw mathematical speed hits a hard wall when it comes to the complex visual media we actually use on our phones today. Here is a physical constraint of a CPU. It is strictly designed for sequential processing. As you can see in this pipeline visualization, instructions must pass through the processor step by step. One exact calculation must finish before the next one can begin. Now, apply this constraint to launching a modern smartphone game. You aren't asking the phone to solve a single math problem. You need to render character textures, calculate the complex lighting, draw the character shadows, and build the environment geometry, all at the exact same moment. If you forced a CPU to handle this, the pipeline chokes. Because the CPU works sequentially, it would load your environment piece by agonizing piece. First a building, then a shadow, then a cloud, making gameplay physically impossible. A single, hyper-fast sequential processor simply cannot crunch enough simultaneous data to smoothly run a modern graphical interface. The math demands specialized hardware. Before smartphone engineers started adding new types of processors, they forced the CPU itself to adapt. To balance raw speed with battery life, modern CPUs adopted what is called a Big.LITTLE architecture. The big side refers to a few physically large, high-performance power cores. These activate exclusively to muscle through heavy sequential tasks, like launching a massive app or exporting a 4K video. The little side refers to efficiency cores. These are smaller clusters that run at significantly lower clock speeds, sipping battery power to handle light background duties, like fetching your text messages or keeping the home screen active. Throughout the day, your phone's operating system acts like a traffic cop, actively shifting tasks back and forth between these two core types, based on exactly what you demand from the device in that second. While this setup is a brilliant way to optimize energy consumption, it doesn't solve the core problem. The CPU still processes data sequentially, meaning it still jams up on simultaneous visual data. To eliminate that visual bottleneck, smartphones require a dedicated graphics processing unit, or GPU, a piece of hardware designed from the ground up to execute parallel processing. Look at this split-screen comparison. Think of the CPU on the left as a single master painter, filling a canvas one brush stroke at a time. The GPU on the right operates like an army of basic apprentices, each painting one tiny square of a mural at the exact same moment. That mural is your smartphone display. The GPU assigns these processors to simultaneously update millions of individual pixels. Individually, these GPU cores are weaker than a CPU's power cores. But because there are so many of them working in tandem, they excel at running repetitive visual calculations in massive volume. By offloading the screen rendering entirely to the GPU, the phone clears the visual traffic jam. This frees up the CPU to go back to what it does best, calculating the underlying physics and logic running in the background. Both of these crucial processors live inside a unified physical ecosystem. This schematic shows the overarching boundary called the System on Chip, or SoC. It houses the CPU, the GPU, and the memory, all on one microscopic sliver of silicon. Understanding this physical layout clarifies a major marketing myth. You have likely heard smartphone makers brag about 4 nanometer or 3 nanometer processors. Originally, that number measured the exact physical distance between individual transistors inside the CPU. Today, that physical measurement is obsolete. The nanometer label is now a generational stamp applied to the entire system on chip, signaling an upgraded overarching ecosystem. And lately, the most critical upgrade to that ecosystem has been the addition of an entirely new district on the chip, the Neural Processing Unit, or NPU, sometimes called a tensor processing unit. The NPU is a dedicated engine built exclusively for localized AI workloads. When running a live language translation, calculates night mode lighting, or flawlessly blurs a portrait background, the NPU is doing the heavy lifting. Without this dedicated unit, your phone would be forced to beam that heavy AI data to a remote cloud server for processing. By handling it locally on the SoC, the NPU dramatically cuts down latency and keeps your personal data private. We can see this entire silicon ecosystem fire perfectly in unison during a single common action, taking a low-light photograph. In the exact millisecond the shutter snaps, the labor is perfectly divided. The CPU instantly registers your finger tapping the button. The GPU renders the glowing camera interface on your screen, and the NPU immediately calculates millions of lighting algorithms to extract a clear image from the dark. Judging a modern smartphone purely by the gigahertz speed of its CPU is like judging an entire corporation based only on how fast the general manager types. It completely ignores the specialists doing the hardest work. Today's computing power relies on the flawless, microscopic coordination of an entire city of specialized hardware, all working in perfect harmony.